Hello everyone, today I am here with the HVAC module, heating, ventilation and air conditioning. This is the technology of indoor and vehicular environment comfort. Its goal is to provide thermal comfort and acceptable indoor air quality. Here I'll take you through a basic case study, that is office chamber, and here I'll start with defining the project name as my office. You could utilize the unit system here. You can change the parameters as per the requirements. Analysis type will be internal forming. I'll exclude all the cavities without flow conditions. I'll check the heat conduction in solids, and I'll change the radiation to discrete ordinates, and I need this absorption in solids to be activated, and I need the spectral characteristics that I'll check, and I'll use the bandwidth that is of 800 to 1800. I need the gravity. I'll define the gravity towards downwards. Okay, here it is towards y direction. I'll make it to y. I'll remove from the z component. Can you able to see there? It's moving towards down. Yep, these are my references, and the fluid. I'll take the air as my reference. You can see there are multiple fluids are available. You could able to use it. Yeah, so solids for the building, I'm going to utilize the hardboard medium. From there I'll just select opaque medium. And these conditions, the default outdoor thermal condition, I'll keep it adiabatic to heat transfer. The coefficient, I'll define it as 12. The temperature of the external fluid, I'll keep it as it is. And thermal and other parameters, I'm not gonna change it. By default I'll keep everything. Okay, so this is a simple office chamber. So I'll just hide the fluid domain here, so it has covered that much area to count. Now to define the boundary conditions, so you can see these all are the double plane glass. You can change the visibility of these all the steps by utilizing the height show options. Utilize the transparency mode everywhere. Okay, now we'll define the boundary conditions. Here I'll just activate the solid materials, so I'll add the solid material. So this is the one. So here I'll define the material solid as, you can see there are different alloys are there, ceramics are there, building materials are there. So right now I'll utilize the steel, that is mild steel for this. The radiation, it should be opaque, and this is the radiator region. So now I'm gonna deal with the radiator cover. For this and the windows pane, I'll define the material as glass. So inside it I'll add this quartz glass, so it should be absorptive. The properties, you can see the spectral graph which I have selected from 800 to 1800, it has taken. Yeah, next thing is to assign the outer wall. I'll utilize the boundary conditions, and I'll use the outer wall from the tab, and here I'm gonna just select the the outer wall regions, and these are the windows which I need into account, and the modes are transparent, so it is taking inside walls into account. So you can utilize the advanced option, that is simply right clicking and select other options to select the window panes here, and do the same for these. And even this is also transparent. You can simply switch to select all the mode, and you can add the value here. It is 20.05 degrees Celsius. Okay, so after that, by just changing the transparency mode of door, I need to define the inlet pressure. So that is I'll change it to environmental pressure by just selecting the inside face of the door, and the environmental pressure as 101 Pascal. And inlet mass flow I need to define, so again I'll make the selection. Inlet mass flow rate is 0.05. I'll apply. Okay, the kg per second is the unit for that. And later on I need to define the heat sources with the volume. So for the person I'm gonna define 32 watt. This is the sample approximation of heat dissipated from the human body. Okay, so now one more is to define the source, that is radiator. I'm gonna select all the faces, that is all the 4+6 faces. You can utilize the advanced mode to select the faces. And you could define the radiative surfaces. The material for this particular component, the radiator, is we'll use this iron casted one. So we have defined the heat sources, and now to deal with the goals, I'll define the global goal, that is the temperature maximum for the fluid and the temperature of the solid, that is maximum. Okay, these are the two global goals, and you can even assign the surface goals for the radiator cover. On the radiator cover I need the total temperature, that is maximum. Yeah, so once we are done with our goals, we can just solve the model by defining the calculation control options. So here we have the solving. From there you can just check these options, that is calculate comfort parameters, and if you want you can add the local mean each. And I'm simply gonna run the study by using the default mesh. It will take some time to give the result, so once we get the results we're gonna just review the results. So you could able to see it will run the number of iterations to get the converged results for HVAC case study. So it has taken 282 iterations to give the converged result here. Here you can just change the transparency of the entire office to review the results. Yeah, in the cut plots you can have the different counters. So that is, now I need the temperature. You can define the temperature range from what to what you want. So from 30 degrees Celsius room temperature to 40 degrees Celsius. So within this range I need the results. It should be reversed, 30 to 40. Okay, and you can use the cursor to the required location to see the results. So this is the first plot which I needed, and you could able to visualize it. And here I'll just change the transparency mode of this particular person, that is human body, and for the same, the radiator covering as well as the radiator. Yeah, you could able to see at that regions how the temperature is varying from 30 to 40 degrees Celsius. This is the first plot which we have plotted now. Well, now we'll plot the one more plot, that is PMV plot. The range should be it should be from -3 to 3. That is the default range. We're gonna just go through that, what exactly PMV and PPD is and how it gonna help us to define the comfort regions. Okay, and you could able to, so this is the region, so where it is varying from -3 to 3. So let's see about this PMV and the PPD, what exactly they are. Okay, here you can see the PMV is the predict the mean value of votes. If there are certain people are sitting inside the office, how many people gonna vote for the comfort region. So it will be from -3 to 3. +3 is the very hot region and -3 is the very cold region. And PPT is the same, that is the predicted percentage of dissatisfied people. So that will also come into account. So how many people are dissatisfied with that particular the comfort region which has been generated, and that should be in the range of 20%. It should not be more than that. Okay, yeah, from the summary you could able to check the details about the study. The ADPI value is 53.8%. Here ADPI is used to measure the performance of an air distribution system within a room or a zone, and it is depending upon these properties, that is air resistor, outlet type, and the room dimensions and all. Okay, that should be on an average of 100%, but the most of the air distribution systems are designed to achieve 80%. Right now we got it 53. In our system we could still make the changes to get the better accuracy or the better ADPI value. Here we can utilize the flow trajectories to just visualize how the air distribution, that is flow distribution, is happening inside the zone or the chamber by just defining the inlet by using the advanced option, that is select of other to define the inside freeze. And here it comes. So we can able to modify the arrow marks, as well as we can increase the number of arrow marks and even the size, and just making some modifications we could get the better visualization of it. So let me make some other changes inside the arrow size. I'll make it 0.01, quite good, and the float should be with respect to velocity or the temperature. Here I'll select the temperature. Better to go with pressure. Yeah, this looks good, and you can even animate this. Yep, this is how the animation gonna look like. You can able to see how the fluid is distributing inside the office chamber. The float is with respect to pressure here. Yeah, finally we can just utilize the animation for these floats, that is temperature as well as the PMV floats. We're able to see how the entire temperature is distributing in the office or the chamber. You can animate multiple plots at once so that you can have a better clarification. I'm gonna have this one, that is PMV float, also into account, and you can even include your flow trajectories. So simultaneously you can have all the things. Yep, that's all about the session. Here we have gone through how to define a sample case study of HVAC module, and we have gone through boundary conditions, how to define it, and how to calibrate the results in the form of PMV, PPD, and APDI. Thank you. Stay tuned.